Not only God knows, I know. And by the end of this story, you'll know too. These were the words of the brilliant physicist Sidney Coleman, whose lectures at Harvard became legendary. Though his name doesn't echo as loudly as Einstein or Hawking, within the world of physics, he was revered, a man of genius humor and terrifying insight. But behind his jovial nature lay a discovery so unsettling, it could rewrite reality itself. For in the late 1970s, Sidney Coleman realized how the entire universe could be destroyed. Coleman uncovered the horrifying truth that our universe may not be stable at all, that we might be living inside a false vacuum. At any random point in space and time, a tiny fluctuation could trigger a catastrophic phase transition, collapsing everything into a more stable form of existence. This wouldn't just end life, it would erase the very fabric of reality, leaving nothing behind. This revelation sparked a deeper exploration into the foundations of our universe, from the smallest particles to the forces that shape everything we see. To understand Coleman's terrifying insight, we must journey back to the origins of modern physics, to the atomic age, the Manhattan Project, and the birth of quantum field theory. After World War II, physicists like Richard Feynman, Julian Schwinger, and others gathered to rebuild science from the ashes of destruction. Their discussions at Shelter Island reshaped the way we see the universe, revealing that everything, from light to matter, is made of quantum fields rippling through space. These quantum fields govern everything. Electrons are not solid particles, but waves in an invisible sea of energy. Forces like electromagnetism and the strong and weak nuclear interactions emerge from the exchange of force-carrying particles, the bosons, that act like messengers between fields. Yet one mystery haunted the Standard Model: where does mass come from? The answer lay hidden within a single, elusive particle, the Higgs boson, often called the God particle. Its existence explained why some particles possess mass while others remain weightless. But the Higgs field, which gives mass to the universe, may also be its ticking time bomb. If the Higgs sits in a false vacuum state, even the smallest disturbance could trigger a collapse, a bubble of true vacuum expanding at the speed of light, obliterating everything in its path. The quest to understand mass and unification became the holy grail of modern physics. Scientists like Peter Higgs, Abdus Salam, Sheldon Glashow, and Steven Weinberg uncovered how the electromagnetic and weak forces could merge into one elegant, electroweak theory. This discovery completed another step toward the ultimate goal, the theory of everything. But buried within this triumph was the grim realization that our universe might be inherently unstable, a fragile balance on the edge of annihilation. Sidney Coleman's chilling discovery serves as both a warning and a wonder. It reminds us that the universe is not eternal or guaranteed, that everything we know might vanish in an instant without warning. And yet, it also reveals the staggering beauty of existence, that from the chaos of the quantum realm, consciousness arose to understand it all. The deeper we peer into reality, the more we realize, the universe is both our home and our greatest mystery. And somewhere, deep within the Higgs field, the clock may already be ticking. In quantum mechanics, everything comes down to probability, the chance of finding a particle in a particular place. This probability is connected to complex numbers, which can be rotated without changing the outcome. This ability to rotate and preserve meaning is what physicists call gauge symmetry, and it's one of the most important principles in the universe. The person who first uncovered the deep relationship between symmetry and the laws of nature was Emmy Noether, a mathematical genius born in 1882 in Erlangen, Germany. In an age where women were rarely welcomed in academia, she broke through with quiet brilliance. Albert Einstein himself once wrote that, in the judgment of the best mathematicians alive, Noether was the most significant mathematical genius produced since women began studying at universities. Noether discovered something extraordinary: when a system's symmetry is preserved, something must be conserved. From this, she proved that conservation of energy wasn't just an assumption, it was a theorem. Shift time, and energy remains constant. Move in space, and momentum is preserved. Symmetry, she revealed, wasn't just elegance, it was the engine of the cosmos. This discovery laid the mathematical foundation for our understanding of forces and fields. The symmetry that governs electromagnetism is known as U1, a type of mathematical rotation that defines how electric charge behaves. But while this explained the electromagnetic force, it couldn't describe the weak nuclear force that governs radioactive decay. Physicists like Glashow, Weinberg, and Salam realized that two new quantities, weak isospin and weak hypercharge, were needed. These described a more complex symmetry, SU2, which operated in a higher dimensional space. Unlike U1, which you can imagine as a circle, SU2 behaves like a sphere, each point representing a possible quantum state that can rotate into another. When physicists combined the U1 symmetry of electromagnetism with the SU2 symmetry of the weak force, they uncovered a unified picture, the electroweak theory. It predicted four force-carrying particles, B, W, W2, and W3 bosons. But there was a problem. As Steven Weinberg pointed out, the equations predicted that all these particles, including electrons and quarks, should be massless. Clearly, that wasn't true. Something had to give particles their mass. The answer emerged from the earliest moments of the universe. Right after the Big Bang, everything was unimaginably hot. Particles moved at nearly the speed of light, making their masses irrelevant. In those first fractions of a second, there wasn't an electromagnetic or weak force, only one unified electroweak force. As the universe cooled, this perfect symmetry shattered in a process called symmetry breaking, and from it, mass was born. In 1964, Peter Higgs and a handful of physicists proposed a bold idea. What if there existed a quantum field, one that filled the entire universe, and as the cosmos cooled, this field froze into a non-zero value everywhere? This field, now known as the Higgs field, would interact with particles, slowing them down and giving them mass. To visualize it, imagine a pendulum. When the universe was hot, the pendulum swung wildly. As it cooled, it slowed down and eventually hung still. For most quantum fields, this meant their energy dropped to zero. But the Higgs field was different. It didn't rest at zero, it got stuck, like a pencil balancing on its tip. Eventually, the pencil fell in one direction, and in that moment, symmetry was broken forever. This was the birth of mass. When the Higgs field fell, the four predicted bosons mixed together. One of them remained massless, the photon, which carries the electromagnetic force. The other three gained mass, becoming the W, W, and Z bosons of the weak force. This was the missing piece, the mechanism that gave the universe its substance. But the Higgs field did more than give mass to bosons. It also gave mass to all fundamental particles. The heavier a particle, the more it interacts with the Higgs field, as if space itself becomes sticky for it. Photons pass through unaffected, zipping at light speed, while electrons and quarks drag through this invisible molasses. This interaction defines inertial mass, resistance to acceleration, the same pushback Newton described centuries ago. However, most of the mass you and I are made of doesn't come from the Higgs at all. Inside every proton and neutron lies a storm of gluons and virtual particles, whirling with energy. Though gluons themselves are massless, their chaotic motion generates mass through Einstein's famous equation, E equals mc squared. So, in truth, your weight is mostly the energy of confined light. When the universe was less than a trillionth of a second old, at a temperature of 1,000,000 billion degrees, this grand symmetry shattered, and the cosmos became heavy. Matter as we know it came into existence. But within this elegant solution, Sidney Coleman saw something deeply troubling. Coleman realized that the Higgs field's energy might not sit in a perfectly stable minimum. Instead, it could be resting in a false vacuum, a temporary state that only appears stable. In quantum physics, nothing is truly still, and even the vacuum can tunnel to a lower state. If the Higgs field were ever to make that transition, it would trigger the most catastrophic event imaginable. A bubble of true vacuum would appear somewhere in space and expand outward at the speed of light, obliterating everything, stars, galaxies, atoms, before we could ever know it was coming. Within that bubble, the laws of physics themselves would be rewritten. No atoms, no forces, no time as we understand it, just a new universe, entirely alien. Whether our universe is truly stable or merely hanging by a quantum thread remains one of the greatest mysteries in science. Experiments at CERN's Large Hadron Collider, led by brilliant minds like Lynn Evans, have begun to probe this question by recreating conditions just moments after the Big Bang. Every collision brings us closer to understanding whether the Higgs field rests on solid ground, or if, somewhere in the vast dark, a cosmic clock is quietly ticking down to the end of everything. In 2008, after years of challenges and breakthroughs, the Large Hadron Collider, LHC, at CERN was finally ready to launch. Normally, such an event would happen quietly under the watchful eyes of scientists, but the LHC's immense power had sparked sensational media coverage. Rumors spread that it might create miniature black holes capable of destroying the Earth. Despite his reluctance, project director Lynn Evans decided to make the launch a public event. As he narrated the moment to the press, the world watched in suspense. Then, to a thunder of applause, the LHC came alive. Protons began racing around its 27-kilometer ring at nearly the speed of light, and Earth remained perfectly safe. Over the following months, the LHC's power increased, and scientists began analyzing the debris from countless high-energy collisions. Among the storm of data, they searched for a pattern, a delicate signal buried in chaos. Eventually, they found it, the faint but unmistakable trace of the Higgs boson. The discovery confirmed a theory first proposed decades earlier by Peter Higgs, that particles acquire mass through interaction with the Higgs field. The finding, dubbed the God particle by the media, became one of the greatest scientific achievements of modern physics, though many physicists disliked the nickname. With the Higgs boson finally observed, scientists could calculate the mass of both the Higgs and the heaviest quark, the top quark, to determine the stability of our universe. The result was both fascinating and unsettling. The numbers revealed that our universe may not rest in a perfectly stable state, but rather in a metastable one, balanced precariously in a local minimum of energy. In simpler terms, the Higgs field could one day collapse to a more stable state, an event that would instantly erase the universe as we know it. But there's comfort in the odds. Current theories suggest that if such a decay ever occurs, it's likely trillions of times farther in the future than the current age of the universe. For now, the cosmos remains calm, its fate hanging delicately on the quantum edge. As physicist Sidney Coleman once wrote, perhaps in the course of time, the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. Until that distant day, we continue to explore, to question, and to marvel at the fragile beauty of existence.